Welcome to a lesson with Dr. Powell. Let's take a look at how we can find a primitive root mod 27. That would be a generator of this multiplicative group, which is cyclic. So the way we do this is we're going to look for two things. One, we're going to look for a primitive root in Z mod 3Z cross, so a generator of this group, and lift that up to Z mod 27Z. Now, why do we look at this group? That's because 27 is 3 cubed. So this is a power of a prime. And in general, we know that Z mod P to the NZ for odd prime P, when we look at the multiplicative group, this is cyclic and has a generator. So we're going to go to the prime, just 3 itself, and find a generator there. So if we can find a generator there, this is fairly simple here, because -1 is a generator of this, and we just lift that -1 to Z mod 27Z, so that when we mod out by 3, we get -1 still, and it works. So we have a lift, -1. Next, we come over here, and we're going to compute E cubed mod 27. Now, why is this 3? Because 3 is the prime. So this right here is 3 cubed. So we're going to take the prime, which is 3. This is a prime, and we're going to put it into this series for E right here. Now, notice as we put 3 in, we successfully get higher powers of 3. This one right here, 3 cubed over 3, just becomes 3 squared. But over here, 3 to the 4th, then you're going to be dividing out by a 3 here. So it's going to become a 3 cubed. And forever on after this, you're going to have higher powers of 3. And so mod 27, they'll just disappear. So we can kind of ignore this part of the series and just stick 3 into this part, and then consider what that looks like mod 27. So we're going to take these two parts and multiply them together and get a primitive root mod 27. All right, so we just take E cubed and then multiply that by a lift of a primitive root in just mod 3 and multiply those together. That's how we can get a primitive root mod this power of a prime. And you can really replace, you can kind of use this exact same pattern for any prime, any odd prime P raised to a power. Okay, so we just put 3 into this series here. 1 plus 3 plus 3 squared over 2 plus 3 cubed over 3. We're going to use the fact that when we divide by 2, we're working in mod 27 arithmetic, which is like multiplying by the multiplicative inverse of 2, mod 27, which is 14, because 2 times 14 is 28. So then we have 1 plus 3 plus 9 times 14, and then this is just plus 9. And this comes out to 139, and use the fact that 27 times 5 is 135. So this is 4 more than a multiple of 27, so it's just congruent to 4. So from this part we get a 4, from this part we get a -1. So if we multiply this 4 and -1 together, we get -4, and -4 is our primitive root, the generator of that cyclic group. Now we can check this using Sage Math. Right here, let's do a loop where we're going to be printing out powers of this generator -4, where these powers actually go from, so they're going to start at 1 and go up to 18. Now, why are we going up to 18? Because 18 is the size of that multiplicative group. The Euler phi function of 27 is 18, or you can just think, take away anything that is a multiple of 3 from the 27 elements, and there's 9 multiples of 3 in there because it's 1/3 of 27 you're taking out. So 27 minus 9 is 18. So there's 18 representatives, or 18 elements mod 27 that where we don't share any common factor with 3. that are co-prime to 3 and sets the size of the group. So we're going to look just through those powers and see if we get the whole group, all 18 elements. And let's see. So raised to the first power, okay, we're going to get 23. And that makes sense because -4 is congruent to 23 mod 27. So this is like your first guy, -4. And then you square it, you cube it, and then you keep on going. And you don't get back to 1 until the end. And look, we've actually gotten all of them. So all the numbers 1 through 27 that don't share any common factors with 27, so ones that are co-prime to 3, we have all of them. So we were successful in finding a primitive root using that little technique. Thanks for watching.